Hey students, this is your Professor Chuck, and I'm going to talk today a little bit about the semantics of TFL. Last lecture, we talked about the syntax of TFL, and so we're really going to get into ways of analyzing meaning today in truth functional logic. Now, just by way of review, just to kind of refresh your memory, TFL is just like CL star, except we have four more operators. All right, so we introduced some new things here. We got the negation sign, which is this lovely little tilde. In fact, I actually discovered something about PowerPoint. You can use a laser pointer. Look at that. Wow. All right, so I'm going to use this thing and annoy the heck out of you. All right, so this thing is the negation sign. All right, and this is the conjunction sign. We got this is the disjunction sign, and this is our good old conditional, of course, and this is the biconditional. Okay, so I also want to get into just a little bit about truth tables. You know, we've seen these for the arrow, and just to kind of review some stuff about what we were saying in the last lecture, right, that negation is true if and only if the atomic formula it modifies as false, right, is actually captured nicely in the little negation truth table. So what you got here, you see, is you have your atomic column listed here, true or false is the two possibilities, and then of course the negation just flips it to the other side. So when P is true, negated P is false, and you can think of negations like truth inverters. They just kind of flip things around. Conjunction truth table, well, you know what, a conjunction is true if and only if both of the conjuncts are true, otherwise it's false. So here we're going to represent P and Q. Right, P and Q are two different formulas. All right, they're two different atomics. These are the four possible ways they could be. Right, the four possible combinations you could have two truths. P is true, Q is false, and then if P is false, Q is true, and then two falsehoods. And this is what it looks like. Right, the conjunction is only going to be true if both sides are true. And in this case, so there's row one, it's true, and then otherwise it's false. So here's something you should commit to memory. Is just the pattern that what this says. Given that it's laid out like this says TFFF, right? You should commit that to memory, right? If you don't memorize what these things mean, you'll just be up a creek, right? You won't be able to do at least the first half of this class at all, and really you won't be able to do any of this class. You got to know what these things mean. Right, the disjunction truth table is just going to be built around the idea that a disjunction is false if and only if both of the disjuncts are false, otherwise it's true. And so here we are, we have the familiar truth table, right? We have the four possible ways. And notice that the only time it's false is if both of the disjuncts are false. So that's going to be the last row right here. All right, otherwise it's true. So these are really easy to make true. All you need is one thing to go true, and the whole thing is true. All right, as opposed to the conjunction, right? Those are hard to make true. Those are demanding. Both the disjuncts got to be. I'm sorry, both the conjuncts have to be true. So they're demanding, but conversely, disjunctions are very easy to satisfy. Right? The biconditional truth table, right, is true if and only if both sides are true or both sides are false. Otherwise, it's false. So here you are, right? Notice that the two times that it's true. All right, you have you got the T when both sides are true, right? And then you got the T when both sides are false. Now, when you have no matching, right, here you have T and an F and an F and a T, okay, now you have falsehoods, right? So you should remember this. This says TFFT, okay, TFFT. Just like, you should remember this, TTTF, okay? Commit those to memory. That'll be on the homework. That's important for you to know, okay? All right, let's move on. And just, you know what? We've talked about models, right? And really, I just need you to understand that there's two different kinds, all right? In CL, for example, we just enumerated the four possible ways the world could be. And then we determined the semantics of our arrow. So here's the four possible ways the world could be, right? You got row one is T and a T, right? TF, FT, FF, okay? And then, we just kind of fill in the semantics for the arrow as each condition is stipulated to us, right? But in CL star, we needed more machinery. I mean, we did make use of this. We kept this around for the semantics of our arrow, but we needed another method. We needed to have something that specified a domain and then extensions for our predicates and reference for our names. And that was a method that we used in order to basically fill in rows, all right? So any method that you have that can fill in a row, right, is a way of creating a model, all right? So the difference between these two methods, these two ways of creating a model, can be formally distinguished like so. So a model for TFL is called effective if it specifies only the truth values for all the atomic formulas. Okay, so that's kind of method one. You just fill them in as you want. Method two is called complete, because what you're doing there is you're just specifying a domain and an extension for all the predicates, reference, and names. All right, so you kind of think of these things like this. In order to kind of get your work done, right, method one is good enough. It's effective, all right? You want to know what the arrow is going to mean under certain circumstances. Well, plug in some truth values and see what you get, right? Once you figure out what all the atomics are in your formula, you'll be able to figure out the truth functional meaning of the arrow formula, okay? Complete, of course, just means that you got to do more work, right? You got to specify a domain and an extension for the predicates and reference for all the names, and that's just a lot of work, okay? And so you can think of that as just being, well, I'm being complete, right? I'm just doing a lot of work for the sake of doing a lot of work. I'm trying to be complete or some nonsense like that. All right, so that's one way of kind of keeping these things distinct, right? Now, models that are effective are sufficient for determining the following logical properties of formulas, okay? Effective models. This is just where you're assigning T's and F's to kind of figure things out, right? You don't need to know about the domain of discourse, and predicate functions, and term functions, or anything like that. Effective models can tell you whether or not a formula is logically true, or false, or contingent, right? You can determine entailment, equivalence, and consistency, all with just ones that are effective, right? So, the complete ones, right, they're necessary. Actually, I don't even know really if this is the case, if they're necessary. In a formal sense, they are, right? In order to determine the actual case of what an atomic formula will mean, right? They are, they're necessary to do. But honestly, right, if you're trying to just figure out what these things are, you don't need to do any of this, right? You don't need to do any of this. But if you're wanting to officially figure out what exactly is the case with respect to some atomic formula, well, then you got to do that, okay? All right, that's what I wanted to say about that. All right, so to use an effective model, right, here's what we're going to do, all right? We're gonna suppose that we want to determine if this is logically true or not. And so what we're going to do is we're just going to use an effective model. Okay, we're just going to assign all the possible ways that T's and F's could be assigned to our atomic formula. So we have three of them. We have FA, okay, then we have KD, and then we have GB, all right? So that's what we're going to do. Now, I know from experience, okay, that there are 8 ways that you can combine those things, right? And I'll tell you kind of why later on, right? But just for now, just trust me that there's 8 ways that you can combine those 3 atomic formulas, okay? Now, what we're going to do then, after we have those 8 ways all listed out, is evaluate how they determine the truth values of the compound formulas they make up. So obviously, right, you got some negations here. You got a conjunction, okay, you got a biconditional, disjunction, another negation. Look, this whole thing is negated, and there's your main connective right there, okay? We got to figure that out, right? We got to solve for the main connective, right? And once you solve for the main connective, and you get nothing but a bunch of T's under the main connective, then it's logically true. And it is, by the way, okay? It is, by the way. And we're going to do this more formally going forward, all right? In the coming days, we'll be doing exercises that does exactly this. I know I'm going through this kind of quickly right now. You can just rewind the video, kind of rewatch it to get a handle on what I'm saying, right? But we'll run through some examples to kind of show you what I'm on about, all right? With adequate models, right, basically, what you're doing here is you're creating effective models to test for logical truth. Is adequate for our purposes, but it's not complete. All right, so An effective model is adequate for the purposes of testing logical truth, but it's not complete. We don't have a domain or a predicate function specified or term functions. Okay? So you basically, I mean, this is just in the book. This isn't super important to know. It's not like you're going to be tested on this, right? But you just have your set of formulas of TFL, right? And a model for TFL is adequate for that set if it is able to assign a truth value to every atomic formula that appears in the set. Okay, so that's just the basic idea, right? So what I want to do is kind of run through an effective test for validity. All right, so what we're going to do here is we're going to isolate just all the atomic formulas that appear in the arguments, right? And so we have 3 of them again, okay? And I kind of get them all figured out. And what I'm going to do is I'm going to create a little table, right? And this is what it looks like. So what I like to do, and this is what I want you to do too, is I want you to put the formulas, the atomic formulas, in alphabetical order. So FA comes first, GA comes second, and then KB. All right. Now, how am I going to fill this out? Well, you notice here I have 8 rows, okay, that I have ready to fill in. Again, when I have 3 atomic formulas, I know from experience that there are 8 ways that you can combine these things, and here are the 8 different ways that you can combine these things. Right, and now I want to say something about this, okay? How did I know to get all 8 ways on each row distinctly? How did I do that, right? That was kind of quick, it's just a slide, right? And I pressed a button, but there's actually a method for doing this. Really what you do is you start from this column here, and you just kind of work this way, all right? And what you do is you just alternate TF, 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 TF until you're done, okay? Then you go over one more, and now you just kind of take 2 at a time. You go TT, FF, TT, FF. And then on this last row here, you kind of divide things in half. You got to get the 4 T's and the 4 F's, right? That will guarantee a way of making sure that you get all 8 distinct possible ways the world could be that will determine, right, the meaning of your atomic formulas. Okay? All right, so with that noted, what we're going to do is we're going to go back now to our problem, right? And when I'm doing an effective test for validity, okay, always try to make your conclusion false, right? And then your premise is true, right? That's going to be your goal. That's what you got to do. Okay, so once I've assigned an F to GA, okay, what I have now done is I am no longer considering the models in which GA is true. Right? Let me repeat that. Once that I have assigned an F to GA, the models where GA is true are gone. Okay, I'm not considering them anymore, right? So remember, right, in order to find out whether or not an argument is invalid, all I need is a single model that shows that the premises are true and the conclusion is false, right? And so I've already eliminated 4 from contention. Now I'm narrowing it down to these 4 that are left. Okay, now I want to make my premises true, so I'm just going to work my way up here. I'm going to start here. I'm going to go to premise 3, okay, and what I'm going to do is I'm going to make that true. I'm going to assign a T to it, all right? So that's what I do. However, notice that it is a negation, okay? So ask yourself, what does KB have to be in order for not KB to be true, right? Well, it's going to have to be false, right? So that's an F there if you can't quite see it, right? That is an F. And so KB is false. So what I've done now is I've eliminated from the 4 possible models under consideration the 2 models in which KB is true, and those are right there, okay? See that? So that was this one, right, where it's true, and this one where it's true. Okay, now it's true in other cases here and there, but those are already eliminated. All right, let's look now at FA. I'm just gonna make FA true. I'm gonna assign FA a true because my goal is to make the premises true and the conclusion false. This is what I'm trying to do. I am performing a test for validity. Okay, so now that I've made FA true, there was just one. So if I made FA true, I've eliminated the case where FA is false. That's the end. So this is the model that I am now looking at. Is this going to prove validity? And the answer is yes, it will prove validity because there is no way for the conclusion to be false and all of the premises to be true, because premise 1 ended up being false because it has a true antecedent and a false consequent. Now, why does it have a false consequent? Well, because it's a disjunction where both of the disjuncts are false. All right, so you really need to know your connectives. Okay, you won't be able to do this if this is what if you don't know your connectives. Okay. All right, now that is kind of a lot of work and kind of annoying, but it is effective. It does do the test for validity. All right, you don't have to make a table here. I just do this to kind of show you, what it is that we're doing, logically speaking, when we're testing for validity. Is what we're doing is we're kind of eliminating models from contention, right? And then if we find one in which all the premises are true and the conclusion's false, well, then there's going to be one left over here. Okay, so you don't have to do this, right? You can use the complete method for testing validity. In some ways, it's also a lot of work, but you don't have to make so many rows and eliminate this and that kind of stuff, right? What you do is you just do the same sort of thing. Okay, what I'm going to do is I am going to be guided by my test for validity. So what I'm going to do is I'm going to assume that my conclusion is false, and I got to be consistent now. Wherever I make an FA false in my conclusion, it's got to be false up here. Okay, that I don't think I pointed that out in the last slide. Right, but now that I have that conclusion false, okay, I need to come up with some kind of model that makes A as F false. And so I'm going to do that. And what I like to do whenever I have to make complete models is specify my domain with positive integers. Okay, I like using numbers. It's really simple. All right, so here we have some positive integers. Okay, and I'm going to make a predicate function for F. All right, and I'm going to put the number 1 in F. Okay, and then I'm going to have, let's see, I'm going to put number 3 in F too. But I need to make A as F false. So A, is going to have to be named, and it can't be an F. So what I'm going to do then is make a term function, and I'm just creating this. Okay, I'm just being guided by what it is that I want here. Okay, what it is that I want. I want a false F. So I'm just creating this model kind of out of thin air, right? There's no rules I'm following. Or all I'm doing is like, I needed a false F there. So what I'll do is I'll make a model that says that it's false. All right, and so that's what I've done. Okay, and now you see that 2 is not in the extension of F, right? So it's false. Now I'm not reasoning from this to get to that. What I'm doing is actually reasoning from this and creating that. Okay, that's what I'm doing. All right, I know this is somewhat tedious, right? But it's to illustrate what's going on with the logic and the tools that we have for analysis. Okay, so now I got KAB, right, as a premise, and I want to make it true. That's what the test for validity requires me to do. So that's what I'm going to do. I'm going to make KAB true. All right. So now, how the heck am I going to do that? Okay. I actually don't know. What do I do? Well, there actually is an answer here, and I'll help you out. Okay. What you do is when I'm going to create a predicate function for K. Now, I actually have to do something very special, though, for the contents of that extension of that predicate, okay? And this is what I do, all right? This actually comes out true. Now, I want you to notice something here that's very special about this predicate extension. Notice that I have this interesting kind of, I have these angled brackets around a 2, and that's separated by a comma, and then the number 3. What this is called is an ordered set. All right, so normal sets are these things with curly brackets, and you just kind of arrange things however you want. Ordered sets don't work that way. Okay, ordered sets are indicated by angled brackets like that, and then the pattern inside of the angled brackets is actually specific. This is saying that 2 comes before 3. All right, and that pattern is reflected in my formula right here. Okay, so this is saying KAB, all right, and here we have A, which is naming 2, and B naming 3. And so what this is saying is that K bears 2 to 3, and so that is reflected here, that pattern, that 2 to 3ness is reflected in the extension of K, and so therefore it's true. All right? So, to review, right? The extension of K is an ordered pair, right? What that means is that 2 must become before 3, right? Which means that A must become before B in, right, the way the names are arranged following after the predicate. So, here's the deal. If K's extension had them flipped the other way around, suppose this is what I had in the extension of K and not this, right? Suppose this is what I had in the extension of K, then line 3 here would be false, okay? Because I would not have the pattern 2, 3 there. I would have the pattern 3, 2, and 3, 2 is not in the extension of K, right? So I hope that's clear. All right, so again, remember now what I got to do is I need to make premise 2 here true. Again, I'm being guided by my test for validity. And I notice that my negation here is in the consequent of my conditional. So I got to make that true, okay? I have to do that in order to make this line true. Because if I have a truth and a falsehood, then it's going to be false, and that's not going to satisfy the test for validity. So then if this negated GA is true, then GA itself must be false. So in order to create a model that shows that GA is false, I'm going to create a predicate extension, right, for G, and I'm only going to put the number 1 in it. The number 2 is not in it, so therefore GA is false. Okay? So what that does then is that makes my negation true, right, which makes my premise true because I have a true antecedent and a true consequent, right? But now that I've made G of A false, I have to make a false up here. And now, okay, this is a disjunction, and I have 2 falsehoods on either side, and so that thing is false. And so there is no way for the conclusion to be false, and the premise is true. Therefore, the argument is valid. Okay? So, look, I understand that some of this is a little weird and a little tedious. What I'd like you to do, though, is run through the test of validity, okay? And just work it out. Now, these practice problems aren't super great, all right? We can kind of just go through them here a little bit. Notice here, there's no way, this is a conjunction, right? So if you're going to make that false, then one or the other of these both have to be false, okay? So you make that false, right? And okay, you know what? I'll just use the complete method. And so that's what I'm going to do, all right? And, there you go. Okay, that's reflected there because 2 is in the extension of G, but it is not in the extension of F, okay? So it's valid. Here, the same sort of issue is going to go on. Here, this model works out. Again, why did I make a model like this? Well, what I wanted to do is make my conclusion false, which I did. Look, H is actually empty. So 2 is not an extension of H, so it's false. And then that turns out to be true because A is not an F. All right, so that I have a false antecedent, false consequent, true conditional. Up here, 3 is not, A is not in G. All right, so that ends up being true. But again, right, I have now a false FA and a false GA, and so it ends up being valid. Okay? All right, you know what? You don't need to worry about this last practice problem, and you don't need to worry about that. So what I do want you to worry about, though, and we'll talk about this, is the homework. Let's get that pulled up here. Homework 4, all right? And let's see. All right, that's good. Let's take a look at this now. What you got to do on this homework is basically, tell me, what's well formed and what isn't. All right, so you gotta tell me if it's well formed, or give an explanation for why not. All right, tell me what the main connective is and circle. Right, that's important. Tell me what type it is too. Okay, a lot of students kind of, what they'll do is they'll just forget to do this part, and then they'll just do this part. They'll just fill in the blank. And that's half of your points off, so don't do that. Okay, some new work. I want you to, from memory, fill in these truth tables. Okay, you got to know those. And then when you're trying to test this for validity, right, just try to come up with a model that goes through that pattern. Try to make this thing false, and then try to make these two things true. And notice that you got a KAB, so you got to use that ordered pair thing. Okay, that's important. You got to use that ordered pair thing, because if you don't, right, you won't be able to evaluate whether or not this is true, given the model that you write down here. Okay, so make sure you do that. Use that ordered pair thing in order to determine whether or not things are true or false. If you don't get that right, and if you don't write it out specifically, right, the way I like things to be written out, you know, using the angled brackets and the curly brackets, I will take some points off. Okay, so just be aware of that. Here you just got to fill in the truth table the way I did it. Okay, so what I'm wanting you to do is practice kind of the TF, 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 and then the double T, and then the 4 T's. Okay, I want you to kind of get used to writing that way, so we're going to be doing that a lot. Okay, and then determine in row 3 of what you wrote down whether or not this thing is true or false. Okay, so that's the homework. It's pretty simple. All right, I hope that this has been somewhat straightforward to you. This can be a little confusing to students, but basically, really what I want you to pay attention to, I think, out of anything in here, is just this angle bracket thing. All right, that's just super important, and writing these models down. Okay, and then just and you build a model off of what the test for validity is, which is the attempt to make your conclusion false and your premise is true. All right, so if you need help, just give me a ring on the Google Hangouts or email me, and I will talk to you later.